we're going to identify geometric sequences. And what we're going to do is we're going to be given data points, and we're going to see if those data points have what's called the common ratio. Hi, so the points that we have are in the sequence known as a table. Is the sequence shown in the table a geometric sequence? If so, write a recursive definition. So we're given some term numbers. And basically it's just n for a number. And this term numbers are usually counted 1, 2, 3, 4, 5 in our case. Then we're given a term. And this is typically denoted by A sub n. A sub n is our output, n is our input. So basically what we're looking at is n would take the place of x, a sub n would take the place of y in our sequences. So our data here is 4, 12, 36, 108, and 324. So the first thing I'm going to do is I am actually going to look to see if I have a common ratio. And the way I do this is I divide, looking for my colors here, I divide going upward. All right, so what I would do is I'd find if ratio 1 would be, or basically ratio 5, would be 324 divided by 108. Okay, so 324 divided by 108, I get to 3. And I would repeat this process, 108 divided by 36. So 108 divided by 36, I get 3. And I would see if this is true for all my terms going from bottom up. So I do notice each one of these is 3 times the next. And this is the relationship. This is my ratio. The sequence is a geometric sequence since we have a common ratio. So when n is equal to 1, a sub 1, which is this guy right here, so we're just replacing this n with this value of 1, a sub 1 is equal to 4. My rate, or my ratio, my common ratio, is equal to 3. And I can write a formula to find A2. So I could say that A2, or this second term number, the value of the second term number, is equal to my A sub 1 times my common ratio of 3. And that is true. If I looked at A sub 2 value, we're looking at 4 times 3, which is equal to 12. That is equal to my second term number's value. And we could continue this pattern over and over again. So I could say A sub 3 is equal to A sub 2 times 3, which is again correct because A sub 3, or this is n, this is A sub n, was 36, and 2 was 12, so 12 times 3 is 36. Okay, and this pattern repeats itself over and over again. So what I can now say is that my value here, A sub n, is equal to, so this is A sub n, we're subtracting 1 to get 2. So if n is 3, we're going to do 3 minus 1, which is 2, times 3. So I'm going to say n minus 1 times 3. Again, 3. The way we get the 2 here is we subtract the 1, and that's why this value is an minus 1. So the recursive definition for the sequence, and this is recursive, there's an explicit. There's 2 different ways we could express a geometric sequence. So this one's going to be the recursor. So the recursive definition can be written as A sub n is equal to 4 when n is equal to 1. And this basically starts off our count because we don't know any of the data value points before 1. We can't assume that a sub 0 is going to be a certain value. So we're saying that we're starting our count at n equals 1. We're starting our term values at n equals 1, and we know that from the data points. And then it's a sub n minus 1 times 3 for n greater than 1. So now we can use this fact that we started with 4 to start determining our data as we go along. So 4 is the first term, n is the term number, so this is the term number, 3 is my common ratio, and the preceding term, an minus 1 multiplied by the common ratio, is used to find the next term in the sequence a sub n. Alright guys, so again, this is the way we write it. The general recursive definition of a geometric sequence is this value. Okay, let's look at another example. We are given the sequence 12, 9.6, 7.68, 6.11, 144, I don't know where I got 1, 1. And we need to determine, is this a geometric sequence? And it looks like it's counting downward. Could be a geometric sequence, but let's find out. So I'm going to take the 6.144. Again, I'm going backwards when I do my division, when I find my ratios. 6.144 divided by 7.68. And I get 0.80. Well, let's see if this is true. I'm going to do 7.68 divided by 9.6. And I also get 0.80. One more time just to make sure. Just to be 100% that each of these follow the common ratio of 8.8, and it does. So now my common ratio is 0.80. So the ratio between A1 so the way I would write this definition is AN is equal to, my leading term here is 12, and that is for n is equal to 1 because this is my first term value. Then I'm going to take my common ratio, 0.80, multiply it by an minus 1, and this is n greater than 1. So a generic way I can write the recursive definition, this is recursive, would be a sub n is equal to curly brackets a1 for when n equals 1. And a1 represents the term value, so in this case it's 12. And then this one would be my ratio times an minus 1 for n greater than 1. All right, so that would be kind of your generic recursive definition. All right, so I hope this helped you guys find the common ratio, find the first term. By the way, this is term 1, 2, 3, and 4. As I move that down, 4. And that helps you get your recursive definition. Like I said, there are 2 of these. They're an explicit, and we will get into an explicit in a later time. But I hope this helped you guys understand the geometric relationships for recursive definition. And if you have any comments or questions, please always feel free to ask, and I'll catch you in the next video.